All right, well, this topic came up earlier, and I realized I might as well just offer you this presentation. Uh, Let me see if I can get it to. By the way, you may notice I'm pretty unprofessional at PowerPoint and stuff. I usually like to leave it in this view where I can control the slides better than the one that fills the whole screen. Anyway, so I gave this talk during the pandemic at the DEF CON, and so it reviews some research I did years ago on Android apps primarily, and it still seems pretty relevant today. And this is, by the way, the reason why I wrote several of the courses, including the one we're going to talk about today. So I discovered that mobile app security standards are terrible. I had heard about this, and that's what caused me to look into it. And I found out that it is really, really bad. And iOS is just as bad as Android. APIs are even worse. And this is ridiculous. And my hypothesis about this is that management is too afraid of technical things, and it's easy to snow them with artificial complexity. The fact is, management should just be asking simple, common sense questions like, what are our secrets? Where are they stored? How are they protected? And if you get gobbledygook for answers, you say, no, don't snow me with gobbledygook. There should be a simple, understandable answer of where did we put the secret stuff and how did we protect it? And so on mobile apps, OWASP has made a top 10 vulnerability. And the ones that catch my attention the most are insecure data storage, insecure communication, insecure authentication, insufficient cryptography, code tampering. A lot of these are available. And in fact, code tampering in particular is almost universal in Android apps. Almost every Android app will allow you to go in and modify the code and make a modified app with malicious content, and the app will still run. There is no reason for this at all. It is technically easy to prevent. And for example, the National Football League had an Android app that you could use to buy, I think, t-shirts or something. And a security researcher found all kinds of flaws and humiliated them. So they upgraded the security of their app. So the National Football app no longer allows code tampering. And in this regard, it is superior to all the apps from banks, insurance companies, and stockbrokers that don't have the right defenses, which doesn't make any sense at all. But the quality of apps is not connected to the importance of the apps at this time. So I just start off with the worst apps I've found. This one here is by far the worst app in the world I ever found. Equity Panda. It is some kind of financial app in India, and they have been around for a while, winning awards and having a certification, although not a security certification. Apparently ISO 9000 is just some kind of functionality certification. And this app is amazing. If you just go to log in to an account, when you try to log in, it will tell you you can't get in because the password doesn't match. But the way it did this was it went to the server with this email address. It fetched the correct email password from the server. Then it compared it to the password you typed in and noticed it didn't match, and it put all that in the log. So if you just look at the syslog in your Android phone, here it goes. Here's the right password. Here's the password I typed in. All transmitted without encryption over the internet. And this is insane. As I see you shaking your head, I mean, the right way to do this is you take the password you type in and you send it up to the server. On the server, you decide if it's correct, and all you send back is a message saying, I'm sorry, your credentials are no good. You can't log in. You don't send the right answer down to the local device. That's just asking for it. And
It
that's what
reminds me of your Appy lesson when you hit the Appy and it just dumps everything it knows instead of filtering it.
yes, and that's coming up. So this was Equity Panda, and I told them, and I couldn't get them to care. This was the University of Houston, but the one I talked about, where you have an alumni app, which, as you know, being college teachers, the alumni are the most important people at a college. They're the ones that contribute money and keep the place going, and that's why football is the #1 activity at the college, because it's the only thing that keeps the alumni engaged. So they made a pretty-looking alumni app where you could look up things, but when you start running the search engine, I saw this running the traffic through Burp. I sent a request to the server, um, and the reply was 351 kilobytes. And I said, how can it take 351 kilobytes to give me like the names of alumni starting with A? And I looked, and it's just sending the entire database down. This is every user, their credit card numbers, their email address, their phone numbers. When you start the search, it just dumps the entire database on the phone. And when I talked to other teachers about this, they said this is a common practice because you might have like slow internet. And so it's better to have all the data right there on the phone so you can get a fast response. I say, well, you could say that, but it has an obvious side effect that you don't want here. Um, So I told them, and like I say, this is the one where I found someone at that school who was in CCDC in the competition. He was a faculty advisor for the CCDC team. And so when I called him, he just said, oh, thanks. And they fixed it right away because you have to get somebody that understands security problems, not a random lawyer or campus official who will probably just freak out and say, you're hacking me. And the answer is to like put you in jail and that'll fix the problem. Somebody on a competition team will understand what a security problem is and what a correct response to it is. So this is those are the worst ones I found. But most apps are really bad. They aren't that bad, but they're pretty bad. So I decided to study what should be the most secure apps in the world. So I went to the top 10 banks, stockbrokers, and insurance companies, figuring these guys are protecting billions of dollars, and therefore they would spend some of that money getting secure apps written. And that is emphatically not true. They spent that money making apps that are pretty to look at and apparently subjected them to no security audit whatsoever. So Bank of America, Bancorp, Capital One, Chase Manhattan, all of these are vulnerable to code modification. Essentially, every app which means you can download the app, you can take it off the phone, change the code to do something terrible, like steal the credit card numbers or passwords, put it back up and use it, and the bank will still accept it as a running app. So all you'd have to do is social engineer somebody who's installing this app instead of the official app. And that is pretty bad. That's one of the top 10 vulnerabilities. I learned about this. Yeah.
2015. Is that the last time you tested them?
Yeah. This years ago since I tested them.
Is it possible they've improved?
It is possible. I went back and tested a few to use them in my classes, and they haven't improved on code modification. They don't yet believe that it matters.
No.
Well, yeah, I think the awareness has not really advanced much beyond this time, although, to be fair, one of these companies did hire me like a year ago to teach secure coding to their coders, which is part of what motivated me to teach a secure coding class. So they are beginning to have some interest in having secure coding. Their current practice has been to have ordinary coders that have like coding degrees write their stuff, and then to hire expensive external consultants to try to fix the security errors. And they're just now exploring the revolutionary idea of actually teaching their coders to write secure code in the first place so they don't have to spend so much on consultants. And to be fair, it's not these banks being stupid. I know the same thing's true of colleges. Secure coding is not considered to be something you teach in college. I don't know if any of you are teaching it. I know our department, I approached the CS computer science department coding instructors, and they all said, we can't possibly cover security. It's a huge, complicated business. I don't know anything about it, and I'm too overwhelmed just trying to teach basic coding. And nobody does this. Facebook approached our college a few years ago and said, we would like to make the world's first secure coding program, and we'd like your college to be our partner to do it. And I eagerly agreed and tried to get involved. And then the department head of my department and the CS department both united to sue Facebook to drive them away, because all they thought is that class will drain students from our other classes. And I've always said, the answer to that is to teach better classes that attract students in. But this is not a popular response among the college teachers at my college. Most of them say, no, the answer is to lock students in like a prison and force them to take our out-of-date classes instead of improving our classes. Anyway, so there is not so actually I know a standard program of teaching secure coding. And when the head of Netflix coding came and visited my class, he said, I asked him, do you want to hire any of our students? And he said, no, we don't hire any students. We don't take any interns, because we know there is no program anywhere, no certification anywhere that teaches you to write secure coding. Therefore, we won't hire anybody until they have 5 years of real experience coding somewhere, because it's only on the job that you learn how to write secure code. And all your college programs are essentially worthless at this. And I don't know if that's still true. I know it's still true at my college. Do any of you have secure coding programs?
We only have it for the advanced classes, not the regular classes.
Well, yeah, because there are advanced classes that have it.
Yeah, we have regular Python and advanced Python. So during advanced Python, they'll touch on security. Yes, they will.
Well, that's something. Okay. Anyway, so so the fundamental flaw here that I looked at is not considered the biggest hazard, but it is the one that is essentially universal. Like more than 90% of all apps on Android have this flaw, code modification. And I learned this when I went to a conference. There was a guy who had like a 2-year-old daughter or 3-year-old, and she was trying to play Android games on like an Android tablet, and the games are too difficult. And he said, I wonder how hard it would be to make that game easier. And he showed how he did it, and I was fascinated. You can suck the app off the phone, you can modify it and put it back so he could make the monsters move slower and make the good guys have more bullets or whatever and make the games easier. I said, you could do that with other apps too. I was amazed. I bet I could do that with banking apps, and you can, and it's not very difficult. And this is something that I think Android developers fail to understand. If you develop software for Windows, or for that matter for Linux, you write it in a language like C or C# or C++ or something, and then you compile it, and then you strip the symbols out and you deploy that. So when people run Microsoft Word, they have machine code, and they can't get back to the source code. All they can get back to is assembly code with the symbols missing, and it's really quite a difficult technical task to reverse engineer machine code in that form. There are techniques, and I teach them in malware analysis class, but the point is, most developers regard it as relatively safe to put secrets in their app code because they're not delivering the source code with the app. But in Android, you are handing out the source code with every app because your apps are written in Java, and Java is a platform-independent language. And what that means is the compiled app is only partially compiled down to bytecode, which runs in a Java virtual machine independent of the platform under it. And that bytecode is easily reversible back into Java, into readable Java, with most of the symbols still there. So effectively, I have the source code for every Android app, and it is easy to see what the developer did. And it's extremely obvious that the developers do not understand this because they put important secrets just blatantly there. So TD Ameritrade, for example, you can go to TD Ameritrade and you can log in with a name and password. Okay. So when TD Ameritrade just puts the password in a log, which in my experience about 10% of apps do, which is of course not right. And that exposes you. They finally fixed it. But Mayo Clinic Medical Transport is another one. I don't know what this is. It's something intended for Mayo Clinic internal use. I think people in an ambulance. It's basically a textbook of medical information, but they put a password on it from this company called Wolf Apps. And I went and looked at it. If you just pull the app off the phone and look at the code, all you have to do is you can pull a app from an Android device with the ADB, Android Device Debug Bridge. You turn on USB debugging and plug into the phone, or you do the equivalent in a virtual environment. Then you can pull packages off the phone. You get an APK file. Android files are this thing, which is nothing more than a zip archive full of code. You unzip it with this tool called APK tool. And now you can look, and all you have to do is now you have all the source code, and you can just grep for secret password and find the secret password to get into that mobile app. So I found this, and I notified the developer, and he told me to get lost and shut up and stop bothering me. And I said, you just volunteered to be homework, didn't you? That's what you did. So that's why I did this. You know, I don't get anything out of this. Nobody fixes the apps, and they sometimes get mad at me. But if they ignore me for 30 or 60 days, then I make them homework. So, because the first time I taught an Android security class, I used like an intentionally secure Android app, and that thing was really old and really buggy and hard to use. And I said, I wonder if I could just find real apps that are vulnerable. And it was very easy to find them. So from then on, we used real apps from real companies right out of the store to demonstrate vulnerable practices, since nobody bothers fixing them. But in order to maintain a good reputation, I engaged in what they call responsible disclosure. I told them and had them ignore me before I just used it for public homework and stuff. So that I seem to have gotten away with that. I felt like so now some of these are apparently actually illegal. The Federal Trade Commission punished Fandango and Credit Karma because they broke HTTPS. This is a common app flaw. Something like 10 or 15% of apps have this flaw. When you make a connection to an HTTPS server, they're supposed to get a certificate, and then they're supposed to verify that it came from a known certificate authority, and they skip that second step. So you can just use a self-signed certificate or a defective certificate. And although your traffic is encrypted, it's not necessarily encrypted with the correct key going to the correct server. So you can put something in the middle like burp, and the app will not notice it. And this is true of a lot of apps. And these two companies were in fact punished for that because they had like a boilerplate statement saying, we secure your data with industry standard encryption or something. And the Federal Trade Commission sued them and said, if you're going to break HTTPS, that is not industry standard encryption. And so they were fined for that. So I include links to this in my reports to apps, hoping I might possibly motivate somebody in the management of that company to say, you know, your security is so bad, you are at risk to be punished for it legally. Uh, and sometimes people will actually fix this one when I tell them. Not very often, though. And then we get the issue of where they store passwords. So when you log in, especially on a mobile device, right, it doesn't make you type in your password every time you open the app. Nobody would put up with that. So it must have remember me functionality of some kind. Or after you've logged in once, you just stay logged in for some long time. In my experience, usually about forever, or at least a month before it makes me put in the password again. So how do you do this? Well, how does your website do it? Amazon remembers you're logged in. Google remembers you're logged in. So how do they do it? The right way is the way the Target Australia app does it. If you log into the Target Australia app, then it will log in like this with a bunch of cookies being set. They have these long random numbers, which is the right thing. And one of them is the authentication cookie. Here, it's a random number, which means nothing to anybody except on the server, there's some database that records which account that number goes to. This is the right way to do it. I thought everybody knew this for years. This is the way web apps work. You store a cookie. The cookie should not be an encrypted version of your username or password. It should just be a random number. And then on the server, I know anybody comes in with that random number cookie, that's this user. That's the right way. Almost no apps actually do it that way. What they actually do is this, like Staples, for example. You log into Staples, and when you do, it stores on the phone something called encrypted password, which is the base 64 blob. Now, right away, you know this is wrong. They shouldn't store your password on the phone anywhere. There's no need for that. All they could do is store a random cookie, which wouldn't be any risk. And so you wonder, why store the password? Now, since I wrote these slides and talked to people, I think I understand why. I think what happened is they had a working system of servers for their web app. And then they asked somebody, make a mobile app, but we're not really going to like spend any money on this or give you the authority or anything needed to do that. Just quickly make a mobile app. And so the mobile app just logs in with your name and password into the web app server. And they didn't somehow connect it to the authentication system so they could have a series of cookies available for the mobile app. I don't know. But anyway, I think it's got to be something like that, sort of a political right-hand, left-hand argument among various divisions of a company. But anyway, this is by far the most common thing mobile apps do. They store your password locally, so every time they launch, they can log in with your password. And therefore, there are extra copies of your password floating around where you don't know about it, like on your phone, which I would argue is a pretty high-value target. You're likely to lose your phone or get malware on it if it's an Android phone. So here's a good Android authority. I thought this was a good list for how to store passwords and other sensitive information. The best procedure is one, don't. You don't need to store a sensitive thing on the phone. If you think you do, just rethink the logic flow of your program and you will realize that you don't really need to store a secret on a phone. However, if you're convinced you have to, there is something called Android Keychain. And there's an iOS keychain. This is the system-provided encrypted storage to put secrets in, and all you have to do is read the documentation and make the right API calls, and you can store it encrypted with the encryption system provided by the operating system. That would be the best thing to do. If you won't do that, you could encrypt it with a public key and send the public key encrypted stuff up to the server, which will decrypt it there. That would be pretty good. The secret key that's needed is never on the phone. It's on the server. However, nobody does any of these things for all practical purposes. In fact, I was pretty horrified by, I think it was the Walgreens app, actually used the keychain for other stuff and then stored your password locally. So what they almost all do is they encrypt with a private key using private key encryption, stick it on the phone, and then they try to hide the key somewhere on the phone. Like, it's just like sticking a key under your mat to your front door. Another thing a lot of them do is store the data unencrypted on the phone. So here, for example, is Staples. Now, when I wanted to measure the quality of this encryption, one thing I tried, which you might understand from yesterday's lesson, is I put in this password, 32 identical A's followed by some other letters. And the point is, if they're using AES in electronic codebook mode, they will encrypt the first 16 A's and get an answer, and the next 16 A's and get the same answer, and then have some stuff at the end. And that is, in fact, what happens. When I use this as my password and then go on the phone to see the stored encrypted password, You can see it's much longer than the previous one because my password is longer. That's already a really bad sign. If they were doing password hashing, which is what you're supposed to do, the hashed password would always be the same length regardless of the length of the input. But in fact, when I decrypt it, when I just decode this base 64, I see there's 16 bytes and the next 16 bytes are identical. So this is the encrypted version of 16 little a's, and this is another copy of the encrypted version of 16 little a's. So this shows they made another basic flaw. They're using electronic codebook mode, which is ridiculous and out of date. And then I read the Smalley code. And I just look for like password and username, which is just sitting right there. Like I say, the names of variables and methods are preserved in Smalley code on Android apps. So it's really easy to find the good bits. So here's the password. They're going to create the thing called encrypted password by calling something called GU and something called M. This is because of a default Android security feature that comes with Android Studio called ProGuard or something. And what it does is supposedly protect your app by changing the names of things to just A, B, and C, and so on. But as you can see, it's completely worthless. It changes the names of a few methods, but it doesn't change the name of methods or variables with names like encrypted password and username. So this is like useless. I've never had any problem finding the good stuff quickly in apps protected by ProGuard. There are commercial tools that really obfuscate your app. One of them is -O, and there are other ones. They cost a few $1,000s, and they change every name of every method and every variable to like 20 random characters. And that will slow down the reverse engineer. You can't no longer find the code that refers to the password or anything. You can still do it. I've done it to those kind of apps. What you have to do is write Python code that will put every single variable in the log, then run the app. It's incredibly slow, then log in, then look in the log to find where the password went. You can do it. It's more painful. But anyway, default apps don't encrypt any or conceal the obvious names of things. So I went to look at these methods. The method called GU and the method called M are apparently used to encrypt the password. So when I look there, what do I find? I find a string object being built with the brand of the phone, a device identifier, a model identifier, the serial number, and then the name of the package. So I wrote here's the actual string created by that. I added a message that put it in the log. They add extra salt, then the name of the phone, the environment, the version of Android you're running, API, and then the name of the app. It takes all that, runs it through SHA-1, and takes the first 128 bits, and that's the key for AES encryption. So, like I said, that's essentially just hiding the key on the phone. The key is just constructed from things that are simple identifiers of the phone, and the end result is I can easily predict the key and decrypt the data. So I went online to verify it's going to work. And then I wrote a Python script that would just steal the data off the phone. And then I notified them, and they didn't do anything. So I gave them a few months to fix it, and then they became homework. And I made videos about it. And then they actually sent me an email saying, "You bad person, did you look at the terms of service? The terms of service say you're not allowed to reverse engineer our app." And I said, "There are terms of service? Oh, I never looked at them. I looked at them, and the very first thing you see in screaming letters is, 'You cannot reverse engineer this app.'" So I called my lawyer. In this kind of work, you need a lawyer. And he said, "They can't tell you that. They can't give you an app and say you're not allowed to inspect the security of this app before trusting it." He said, "That's fair use." So I just completely ignored them, left the videos up, and they didn't do anything. So anyway, my students have been stealing my credit card number out of my Staples account with this technique for a while. It's a homework assignment in my Android course. Anyway, so I notified. Now, however, then I gave a talk in Washington, D.C. I went to a conference there which had like government officials and NSA people at it. And I was demonstrating this stuff. And right before I went there, they fixed the Staples app. When I tried to demonstrate this live, suddenly my attack no longer worked on the Staples app. However, I never have bothered to research it. I'm pretty sure they did not fix the data storage problem. What they did was block it from running on rooted phones. Now, to do this stuff, you have to root your Android phone. This is, by the way, not a bad security measure, but it doesn't remotely address the real issue here, which is all the users have their password stored locally in an insecure manner. But it does mean that my exact demonstration won't work anymore. And this is something researcher Bennett Shaw put up on Twitter years ago. I thought it was a good answer. This is for diagram explaining, we have patched the vulnerability you reported. this is what tends to happen. They put a barrier in that stops that specific attack, but they haven't actually fixed the fundamental problem at all. Anyway, so I looked at other ones, things that just store your password in plain text. McDonald's, Menards, Ace Hardware. It's just stored right there on the phone like that. Plain text login, where they don't even encrypt it in passing. A couple of apps. Here's the 7-Eleven app sending unencrypted traffic with your password over the internet. This is kind of amazing that this still happens, but it does. Then this one was pretty great. My college makes us go to meetings occasionally. At least they used to back before the pandemic when everything was face-to-face. And they made me go to this required meeting, which was absolutely worthless and boring. But I completely ignored the meeting and was hacking things in the back. And I remember this is the greatest meeting ever because I found a flaw in Amazon, or I thought I had. This price tracker for Amazon breaks SSL. You can send it through Burp and it doesn't notice. And I said, wow, there's a security flaw at Amazon. But then I realized this is not an app from Amazon. Now, there's something people say, and I guess it's true, that different Amazon people see different prices. And the price changes frequently. So what this does is it will log in with your Amazon account and check the price of something and wait until that price falls to a low enough value, and then you know it's time to buy it. That's what this does. It's not an official Amazon app. So it needs your Amazon password. It needs to send it up. And they chose to send it with broken HTTPS. So I contacted the developer and he replied to me. I said, hey, your app doesn't verify the certificate. It accepts an invalid certificate. And he said, yeah, I just put that in last week. It's great, isn't it? And I said, wait, that's not great. What are you talking about? He said, yeah, it's great. What was happening is people were getting these blank screens on Android. They couldn't get through to things. And I found what the problem was. It was that encryption stuff. So I turned that off and now it works great. And I'm like, dude, you can't just turn off a fundamental security feature of the operating system just to solve a usability problem. He said, well, I guess not, but I don't think he ever fixed it. But that was his point. He fixed a bug causing certain viewers to see only blank screen. That bug was HTTPS being implemented correctly. By turning off the HTTPS verification, that bug went away. He was proud of this. And, anyway, then there's ones that store your password with reversible encryption, which is, an AES key hidden on the device like those other ones. A lot of ones, Home Depot, Kroger, Safeway. And by the way, there's about 20 grocery stores that are all Safeway, Aldi, all the ones, and their apps are all the same. And they all store it with the same kind of encryption. They just have a bunch of different names to make it look like there's not just one monopoly running essentially all grocery stores. Home Depot, the locally stored password is encrypted, and I found that the password was something predictable, and so you just need a few lines of Python to decode it to get it back to the original password. And by the way, you can see they're using that form of padding, 1, 2, 3, 4, 5, 6, 7, 8, the kind we talked about yesterday. If you have 8 bytes of padding, that should be a 0.8 padding it. PKCS number 11 or something. And so this is the script to decrypt the password. I wrote a bunch of these. I would send them a vulnerability report saying, dude, your password can be reversed with this script. And you shouldn't be doing this. And nobody seems to care, but I would tell them, here's Walgreens. Same thing. It really only takes a few lines of, in this case, the Walgreens user data encryption key is always the same. It's just a password derived from this, a fixed hard-coded thing, which is then run through a password key derivation function. And that's Walgreens decrypting a password. Then there are ones that have a bunch of vulnerabilities, like Delhaize and Public, the passwords in the log, broken SSL, and insecure local encryption, that sort of thing. And there's a few that fixed them, very few. Like I say, the odds, this is called white hatting, warning people about vulnerabilities when they didn't ask you. And I found my general success at this is 2% of anybody actually caring and fixing anything, but a few of them fixed things. And in fact, the sporting goods store, Dick's, I think that's the one. They fixed things, promised me a t-shirt, and then didn't send me a t-shirt. But anyway, at least they fixed it. Then I wonder how bad iOS apps are. iOS apps are not written in Java and compiled to, they're not really distributed, containing essentially the source code the way Android apps are. So that's kind of nice. You have to do reverse engineering from assembly code. And Joe McRae, who is a really great teacher, gave a good talk explaining how this kind of exploit development, this kind of reverse engineering from binary code is not really that difficult. And I found this very inspiring, and I learned how to do it and wrote some courses teaching people how to do it. So it can be done. And Georgia Weidman, his student, wrote this book, which is very good and contains the best explanation of how to make a buffer overflow and understand binary exploits. And that got me started. All the other famous books on the topic have step-by-step instructions that absolutely do not work. They're too out of date. They use obscure versions of Linux. They skip important steps. This is the first one I found that actually explains something in step-by-step so you can do it. And anyway, so I wrote an exploit development class after I learned how to do it, and I have a bunch of projects there that are easier to do. And when I taught this class, a Google software engineer took my class and then spent $5,000 to buy the professional version of IDA Pro with all the plugins and spent 2 months analyzing the bootloader of iPhones and developed the first iPhone jailbreak I mentioned in 7 years, the only new one, Check Rain. This guy going by the name of Axiom X was in my class, and he went and did this. Not that I taught him how to do that. I just taught him the very fundamentals of how to do some reverse engineering, and he roared ahead and wrote this thing, which is the most important jailbreak in years. So then I went to look at Blue Cross Blue Shield. I was doing insurance apps, and I discovered that Blue Cross Blue Shield seems completely disorganized. There's not one national app. There's not one national database. Every local branch writes their own app. And by the way everybody writes an app is they hire one of like 3 companies who uniformly outsource it to Bangladesh or something, where they use sort of cut and paste procedures. So I see all the apps look pretty much the same. There's about 3 categories. Anyway, so this one here stores passwords insecurely. This Blue Cross, this one doesn't validate TLS certificates, and so on. Many of the Blue Crosses had different vulnerabilities. They all seem to be independently writing their own app, so they're random. And then I started looking at colleges. West Point's app was insecure, and the Air Force app was insecure. So I checked. These are written by a company called Straxis, and their entire product line was insecure. So I contacted them, and they said, well, you shut up about it for a couple months so we can fix it. And they did. They fixed their entire product line, which is a whole bunch of colleges, bought apps from these. They all look good, but they all transmitted passwords insecurely. And Zillow caches passwords insecurely. And Stock Options sends plain text passwords over the internet. And I was surprised to find modern iOS apps sending passwords insecurely over the internet, because I had read that the Apple iOS app no longer allowed this, their operating system. So I went and read the detail. I found modern apps sending passwords unencrypted, and I said, I thought that was forbidden, so because of this, preventing insecure network connections. But then I read into it, and it's not really preventing it. What it's doing is by default, it won't send insecure data, but you can turn on a parameter to turn that off if you want to. So apparently these app developers have done that, and I understand how it works. They had an earlier version of the app for the early version of iOS, then they upgrade something. They say they broke my app. Oh, I just had to make this adjustment to make my app run, just like that guy with his Amazon price tracker saying, what is this encryption junk anyway? Turn that off and the app will work better. And of course it will. The functionality will be improved. It'll have less errors for the end user as long as you don't care or understand that there's a side effect. So there can still be iOS apps sending unencrypted passwords over the internet, and they're out there. So then I tried my college's app, and it turns out to come from a whole line of vulnerable apps. This is made by another developer, and a whole bunch of the colleges have similar apps, all sending it with broken encryption. And Jack Henry and Associates has another whole line of banking apps that all put passwords in the log on the phone. And there's another series of banking apps that all expose passwords and logs on the phone. I contacted these developers. I'm not sure whether they fixed it or not. Anyway, all you have to do is get any list of apps, and you will find amazing vulnerabilities if you do very simple audits on them. And so I made this hacking mobile devices class to understand this. This is another one of the standard textbooks everybody uses. And I made a cryptography class, realizing it's painfully obvious that nobody, not the developers nor their managers, understand the basic concepts of encryption enough to ask, did you use public key encryption or private key encryption? If it's private key, that means there's a secret key. Where did you put that secret key? How do you know bad people aren't stealing that secret key? You should be able to get answers. And that's why I say management should be able to ask these questions, simple questions, and you better get simple answers you can understand. And if you don't, something is wrong. Do you need to keep the data at all? Is it encrypted? How did you encrypt it, and where is the key? There should be simple answers you can understand to these questions. And it is very obvious that people are not doing this. So anyway, that also led me to write the secure coding stuff I'll show you today, which is based on what I was teaching people inside a bank for maybe 6 months. They haven't called me back in about 6 months. And what I suspect has happened is the upper management has said, wait a minute, rather than teaching our programmers to code better, everyone's going to use AI and we'll just fire all those coders. That's probably what's happening. They're probably considering that. So I probably have to wait for them to finish having that crash and burn before they'll call me and want those classes again. And I think it won't take long from what we've seen looking at the performance of AIs here. I think the management thinks I'll fire everybody and replace it with AI right now. And within 6 months, they're all going to get over that after discovering that the AIs aren't really up to the job. So that's what I wanted to show you here. I'll stop this one.